So good morning to all of you. So here my talk is on shape memory alloy actuated low frequency astable electromechanical multivibrator, and it is not actually about the sensor, something like about the actuation and electromechanical actuation. Okay, so go to the introduction section. Now motivation of this design. So before that, we have some kind of electric motor or some kind of shape memory or smart material based electromechanical devices we had already. So something like you have to supply some amount of electric voltage or some kind of current. There should be some kind of mechanism and some actuation, some motion. But here we were targeting something like a simplest mechanism to to convert the electrical energy to get some kind of mechanical energy. Now here we have three terms: oscillator, resonator, and multivibrator. So here you can see that this is all about the multivibrator. So oscillator and resonator. So here you can get some kind of sinusoidal oscillations also possible to get when you have oscillator and resonator. But multivibrator is something like when you have two different states, so it can switch between two states. Okay, it's like not like a sinusoidal, basically kind of pulse generator. And this is an electromechanical multivibrator. So now the shape memory alloy. So some basic stuffs of shape memory alloy. So it can originally remember the shape, and after that it has can see that two shapes are there, like shape memory effect and the pseudoelasticity. Two effects are there, and at high temperature it shows a austenite phase, and low temperature it shows a martensite phase, and then after that, so here you can see that. So what we have used here, so shape memory exhibits electrothermomechanical property, which is used for this application. Okay, so electrothermomechanical means now I have a shape memory, I will supply some amount of electrical power, so that will increase the temperature of the shape memory, and after that we'll get this type of actuation. Now, and the second figure, you can say that you can see that we have some configuration now to use the shape memory actuator. So first one is a one-way actuator. So here you can see that we have a shape memory. If we are pulling this mass, so here you can see that if we increase the temperature, if the spring deforms, if you increase the temperature, it will contract. The second one is known as the biased actuator, where the first one, so left side you have the shape memory, right side you have the normal spring, elastic spring. So if you increase the temperature, the deformed shape memory will go back to its original shape, and then after that the spring will deform. And the third one, in both the sides you have a shape memory. Now for this application we have used basically the second one. So this is called the biased actuator to get this actuation. So here the biased actuator configuration we have used, and sorry, okay, and we have again some means to supply electric energy to increase the temperature. So some means are there. So here you can see that the first one is directly hit up a shape memory alloy. Second one, you can expose this one to thermal radiation. But the C and D, both the options are related to electrical power. So one is you can directly pass some electrical current through the shape memory, and the second one, you can wrap a shape memory alloy with some wire, and you can pass the electric current to increase the temperature. So here we have used option number C. So we have used shape memory alloy spring, and you have passed the current through that spring. Now here multivibrator, as I told, that multivibrator, that is basically we have two states. It basically switch between two states. We have three types of multivibrator: astable, monostable, bistable. But here we have targeted to design astable multivibrator. So here is the basic design, the simplest design, which will be used to to synthesize this one. So basic design means now the first option. So the first one, at the top you can see the elastic spring. At the bottom you can see the shape memory spring. So here we have a bistable mechanical switch, and this bistable mechanical switch that is connected electrically now. So here you can see the second, the figure B now, where you have stretched both the strings, and after that now it is connected. Both the springs are connected together, and now you can see that the electrical path is closed now here. Okay. So electrical path is closed here, and here you can see that when the electrical path is closed, some amount of current will flow here through this, so that will increase the temperature. So for that, it will change the shape and it will go back to original shape, the shape memory alloy. It will come down. Then after that, here you'll find that now this spring, now this is stretched now. So when the spring will cool down, then it will go to martensite phase, where the stiffness of this shape memory alloy, that will come down, and the top spring, this will now pull it up. Okay, so this is the simplest mechanism to get this actuation. And here you can see that, so this is with a DC source. We have DC source, and here you have the AC source. So actually both the things are possible, because anyway that the current generation, that is basically because of the Joule heating, so it has nothing to do with the frequency directly here. So it will work for both the cases. So we have two designs here, and this one is the simplest prototype what we have tested, and uh, these are some data. I mean, the specification of the design, we have used nitinol spring, and so some relevant data here. And after that, this one is the behavior of the switch. So so the switch, bistable switch, when it is in off state, so it requires 1.12 Newton to pull it off, and requires 1.08 Newton to pull it on. And after that, we have the switch lever arm. So lever arm, so here you can see that if we go back, so here you can see that, so from point A to D, so this is known as the lever arm. So this is important to decide, because it's actually going to apply some kind of moment to pull it down. So finally, after the experiment, so here you can see the result. So this is in switch on condition, this is in switched off condition. Okay, so switch on condition means, now here you can see that when it is in on condition, so huge amount of current will flow through the spring, and because of that the temperature will increase, and because of that again the switch will come down. If we go back to the design here, so here you can see that when the switch is on, then a huge amount of current will flow through the spring. Because of that, it will come down, but it will take more time to cool down. So that is the reason the off time is more than the on time. So if we see this graph, we can see that the off time is more, because it will take more time to cool it down. And here you can see the response, the exponential response. Now the shape memory alloy, it's a spring. So as is the spring, this can be more modeled as a inductor and a resistor in series. Because of that, it has this type of exponential relation. And finally, this is the output result from this one. So so basically, it's a low frequency application. So here you have, now the frequency is very less. But if we use if we bias this one with two shape memory alloy spring instead of taking one elastic and another shape memory alloy, we'll get a better response for this. And the conclusion is, so here we have designed a shape memory alloy actuated astable electromechanical multivibrator, and this multivibrator can be operated by DC and AC both. And this is a very simple mechanism with bistable mechanical switch. So if we supply DC voltage, it'll get flapping on the other side. So to get some kind of low frequency flapping actuator, it's a very simple mechanism. Okay, thank you. And if you have any questions, I can answer.